let's see if we can apply what we learned in my geometric series derivation clip, and let's see if we can solve an actual problem with it. So let's say we have a series of 1/2 plus a 4th plus an 8th plus a 16th plus 1/32, continuing on all the way down to 1/2 to the n. Okay, well, what can we do? Let's start by describing the nth term here. Well, this is just a geometric series, where the first term is a half, and we can say that this can be described by 1/2 times 2 to the n minus 1. This is our a times r type of format, because we're going to begin with the half, and then in each subsequent term after this is going to have a half multiplied onto that, but it's got to be offset by 1 because we begin with the half. So if we combine this, then we would get that this is the same thing as saying 1/2 to the first times 2 to the n minus 1 equals 1/2 to the n minus 1 plus 1. So the minus 1 plus 1 cancel out, or 1/2 to the n for whatever our nth term happens to be. So that's what our terms can be represented as for the nth term. So now let's say we want to add an infinite amount of terms. Well, then we would be interested to know what the summation is for x equals 1 to n, but actually there's an infinite amount of terms, so let's go ahead and set the limit as n approaches an infinite amount to make sure that that goes arbitrarily large as we can have it go. And we're going to say 1/2 to the x here. So how are we going to go about adding this? Well, let's use the formula that we came up with in the other clip, which we came to the conclusion that it was s equals r to the l, or rl minus a divided by r minus 1, where r is our common ratio, l is the last term, and a is the first term divided by common ratio r minus 1. So what do we need to be able to figure this out? Well, r, the common ratio, we need to know what that is, we need to know what the last term is, we need to know what a is, and if you know that, then you can plug everything in. So a, we can see is 1/2, okay, and the last term is going to be 1/2 to the n, but we know that n approaches some infinite amount, so L has to equal the limit as n approaches the positive infinity of 1/2 to the n, which we know that that's going to become 1/positive infinity, or essentially that part is, it's like saying we're going to 0, basically, for that piece. So, okay, and now for the common ratio, notice how each term here, it has to be multiplied by 1/2 in order for us to get the next term. So r equals 1/2 as well. So now, if we take this information, then we find that s equals 1/2 times essentially 0 minus 1/2, and then common ratio of 1/2 minus 1, and 1/2 times 0 is 0, so that's going to get us to minus 1/2 divided by minus 1/2, or by 1/2 minus 1 gets us to the minus 1/2, and we find that the answer is 1. Well, how can we make sense of this? Because we're adding an infinite amount of terms, yet it somehow converges to a finite answer. Well, if we look at it from a geometric interpretation, where we have a square with side length 1 all the way around, then this would basically be like saying, let's take a square where the area is clearly 1, because it's 1 times 1, 1 squared is 1, so let's divide it by 1/2 to get the first term. Then we're going to have dividing it by 1/2 again to get the next term of a fourth. Then you'll see that if you keep trying to divide it by 1/2, then no matter how many times deep you want to go, then every single term that you could ever come up with in the series can of course squeeze into a square with an area of 1, and each term represents a bit of the area, and each piece, including the infinitesimally small last piece, gets squeezed into this square of area 1. So this is just an interesting problem that I remember when I was learning this in school, so hopefully this demonstrates the power of being able to add an infinite amount of terms, and sometimes it'll even converge to a single finite answer. So yeah, hopefully you found this video to be very instructive, and I'll see you in the next one where Joe shows you how